Hello students, today we are going to see D flip-flop, that is the 1-bit memory of digital systems. How does a processor remember a bit? Let's understand the magic of D flip-flop. So what is D flip-flop? D flip-flop is a digital memory element used in sequential circuit to store 1 bit of data. It stores the value of D only when the clock edge occurs. Let us understand the signals. That is, you see D, it is data input, CLK is clock signal, Q is output. That is, clock is permission signal, D is data to be stored, and Q is stored memory. When the clock edge occurs, the value present at D is copied to Q and it is stored until the next clock edge occurs. And let's see the behavior, the same thing. That is when D is equal to 0, after the clock edge, Q becomes 0. If D is equal to 1, after the clock edge, Q becomes 1. So the flip-flop remembers the value of the D at the clock movement. This is the tabular column, that is, you see when clock is rising, if D is 0, Q is 0. And when the clock is rising, if D is 1, Q is 1. So when the rising edge of the clock, the value present in the D is copied to Q. Q holds that value, it remains stored until the next clock edge occurs. It does not continuously follow D. It updates only at the clock edge. Now let's start our RTL code. First we are giving the module and we are giving the module name. That is, it defines a hardware block named basics underscore sequential. And then we are giving the input clock. CLK is the clock signal. It controls when the circuit updates. Without clock, no synchronization. This makes it as a sequential circuit. Next, we are giving the input D. D is the data input. This is the value we want to store. It is either 0 or 1. Now, we are giving the output. Q is the output. It is declared as reg because it stores a value. It is assigned inside an always block. The important thing is reg does not mean hardware register automatically. It means it can hold value inside procedural block. After assigning the inputs and outputs, we are closing the bracket and then we are starting the operation. That is, always. This block runs repeatedly during simulation and it is representing hardware behavior. And this at postage clock, nothing but it is a very important thing. It executes this block only when the clock edge rises from 0 to 1. Triggers only on rising edge. And this makes it edge triggered, flip-flop behavior and synchronized design. And we are beginning at, look at this, Q less than or equal to D. Here less than or equal to is non-blocking assignment. It means that it stores value of D and updates Q at the end of timestamp and avoid race conditions. This means on every rising edge of the clock, Q next is equal to D. So this behaves exactly like a D flip-flop. Now, after completing everything, we are going to close the always block. And then we are ending the module. Now we are going to write the test bench. First, we are going to give the module and module name. After that, we are assigning the inputs and outputs using reg and wire. First you see, we assign the input using reg, that is clock must be reg because we manually toggle it. And look at here, the input D is given by reg. This input must be reg because we assign values in initial block. And next you see wire, that is output we are giving it wire output from device under test. That is, we do not assign it directly. So we are giving it as wire. And next, after assigning the inputs and outputs, we need to do the instantiation. That is, first we are giving the name of the RTL module which we have given in the RTL code, and then we are using the unit under test and we are opening the bracket, and then we are connecting the input clock of test bench with the module clock. Same way we are connecting the input D with of test bench to the module D, and then test bench output is connected to the module output. After instantiating, we are closing the bracket, and after completing the inputs output assignment and instantiation, we are going for clock generation. That is, usually we give the test cases. Here before giving the test cases, we are giving clock generation. Test case, first we are beginning it initially, and then clock equals to 0. That is, initializes the clock signal to 0 at the time t is equal to 0. This ensures known starting condition. And the next, forever #5 clock is equal to toggle clock. This is the art of clock generation. Here this forever is infinite loop. It runs continuously, and #5 is wait for 5 time units, and this clock equal to toggle clock is invert the clock. Here clock changes every 5 units. So clock period is equal to 5 plus 5, 10 time units. This creates a 50% duty cycle clock. Now, after assigning the clock generation, we are going to end it. Look at this, we are ending it. Now we are starting the test simulus. First, we are initially beginning it, and we are initializing the input. That is, first we give D is equal to 0, and then we apply the test cases. The first test cases, after 7 time unit delay, the D is equal to 1. That is, at time t is equal to 7, change D. And then the next test case is applied. That is, at 10 time unit delay, D is equal to 0. Next test case, at 10 time unit delay, D is equal to 1. And the next test case is we are applying is at 10 time unit, D is equal to 0. After applying all the test cases, we finish the simulation after 10 time unit, and then we are ending it. Now we are giving the monitor block, and we are initially beginning it. Look at this. This monitor, it is for continuously printing values whenever any listed variable changes, and it automatically updates the outputs. And look here, this percentage 0t is simulation time, and this percentage b is binary value, and this $time, this is built-in system variable. It returns current simulation time. So this monitor block is for continuously printing values whenever any listed variable is changing. And then next we are ending the monitor block, and now we are ending the module, and let me summarize it. First, we are giving the inputs and outputs using reg and wires, and then we are instantiating the module and the test case. After that, we are generating a clock signal for producing a 10 time unit clock period, and then we are giving the input D is initialized to 0 and then changed at specific time intervals to test different input conditions. Here, on each clock edge, the sequential circuit updates output Q based on the value of the D. Next, we are going for this monitor block. This is for continuously printing time and signal values during simulation. And then we are ending the module. So this is the test bench of D flip-flop. Students, today we have seen the D flip-flop and lot more codes are there. If you want to learn the RTL code from the scratch, please subscribe my channel. Thank you.